Okay. Thank you. Yes, so let me first say it's a great pleasure to be here in Singapore and a great honor to be asked to be a distinguished lecturer in the same sequence of Mel Levy. And I think this is a wonderful meeting that we're having so far. And I think it's going to be very productive. So I will give one lecture now and then one on Friday after lunch, I think, or maybe about lunchtime. And this first one, I'm going to review a bunch of material that I've worked on for the last 12 years or so. And some of you will have heard bits of it, but I want to sort of present it all together. And then I'll show some very new stuff in the second lecture. And it's all to do with this semi-classical origins of density functional approximations. And this picture that I made a few years ago is supposed to represent these books. These very heavy books here are all the books on many-body quantum mechanics that tell you that solving for many interacting fermions is a really hard problem. On the right here, we have about, 2 hours worth of DFT papers that the world produces every couple of hours or so. It produces 40,000 a year at the moment, at least. And then this little envelope here is what the kind of size of, I forgot to bring the envelope, right? But you can write those density functional approximations basically on the back of an envelope. So how is it that very simple little approximations, many of which we've seen in the last week or so, can give us useful answers to this quantum many-body problem? That's the question I want to address. And many of us were fortunate enough to know Walter Kohn, who passed away a few years ago, and one of his mantras was to ask the right question. The important thing was to ask the right question. And I'm going to claim that I'm asking the right question. So how do we derive density functional approximations? Many of us in density functional theory love our exact theory of DFT, but it doesn't tell us directly how to make approximations. And we'd like to derive them in the same way you derive them, say, for perturbation theory. You know how to do perturbation theory. You know the rules. People doing traditional quantum chemistry can do couple cluster expansions. And they know what they're doing, and they know what terms they've left out. And they know that if they had a big enough computer, they could evaluate those terms, right? And they can study the behavior of their expansions. But if you notice, I really noticed this at a meeting I helped organize in Santa Barbara, where we did excitations of materials, and it was very clear that the people working in density functional theory spoke a totally different language from all the other theoretical physicists, whereas they had a common language. I used to try to tell them about our stuff, right? And I'm going to focus on the leading correction to local density approximations. So Thomas Fermi theory, mean field theory as well for the interaction becomes relatively exact. What are the corrections? And I would say our present best methods are reverse engineering and a certain style, John Perdue. John Perdue, as far as I know, is the most cited physicist of all time, much more than Phil Anderson or Ed Witten or anybody else, because he has developed more of these approximations than anybody else. And he uses exact conditions of quantum mechanics in order to avoid fitting. And for an example would be, say, the PBE exchange is a very simple form. And it doesn't have any parameters fit to any specific system. And you could think of Bekke 88, more popular in chemistry. And but Bekke fitted to atoms, and including looking at evanescent regions, which will turn out to be relevant. So these are sort of just typical examples. Okay, so here we have many different communities. Well, basically 3, more or less. So we have sort of math and mathematical physics of a very rigorous kind, of the school, let's say, of Lieb and Simon. and Heinz Siedentop, one of our organizers, is one of the main people in this field, and Jan Philipp Solovej, and so forth. Semi-classical physics of a traditional type are expansions in h-bar, although we'll see that you have to be a little careful when you say that. But Gutzwiller, Martin Gutzwiller is very famous, Michael Berry, Brach, Heller, and then these are used in many different branches of physics. And in chemistry, a lot of nuclear dynamics where quantum effects are important are done semi-classically. And then we have electronic structure theory, density functional theory, and sometimes it overlaps with quantum chemistry. And you have ab initio methods in quantum chemistry. We distinguish ab initio from DFT, meaning traditional wave function type expansions, and perturbation theory. And in materials, we're often more interested in response properties. So we have GW, dynamical mean field theory, and so forth. But again, these things look quite different from density functional theory. Again, because they're sort of solving the quantum mechanics the way we're taught in our textbooks. Now, I want to bring attention to this old book. I don't know if anybody's ever heard of the author here. This is a brilliant book. It's a sort of testament. It summarizes work of our organizer with Julian Schwinger. It's clearly a sort of labor of love. And the tricks that are developed in this book are just fantastic. It's just a joy to read. It takes a little effort, I would say. And we'll get back to that. But part of this is an overlap of two communities. There are semi-classical ideas about the degeneracies of states and the smoothness of curves and things like that applied to Coulomb interacting atoms, right? So this is a region where these two overlap. Not too many epsilons and deltas in terms of proving things, but fantastic calculational things. And we'll see an example. Okay, so now I'm going to do a series of simplifications. Now, my goal here is to offend everybody from every community, right? Because I'm going to simplify it in some way that you will say has simplified it too much. And then I'll argue that I haven't. So here I have particles in a box with a potential at the bottom of the box, right? A V of x, but a finite box. And I can, with Mathematica, I can solve this in 5 minutes and get eigenvalues. And here's a water molecule, the density of a water molecule. And here I have 5 different games I'm going to play. This is one-dimensional. The real world is 3 dimensions. Here I have box boundary conditions. The real world is either open if you're a chemist or periodic if you're a materials person. The number of atoms, right? The number of centers, let's say, right? A lot of people like to study the atoms because it's simpler, because it's spherical, but then it gets more complicated. Most molecules have more than one atom in them. Smoothness of the potential, right? The real potential is Coulombic, and it has a whole bunch of issues, but we're going to just look at smooth potentials and of course, the interaction strength. So in density functional theory, we just heard about the adiabatic connection formula. So if lambda is 1, you get exchange correlation, and the limit as lambda goes to 0, that gives you exchange, and if lambda is equal to 0, you have no interaction between the particles, but they are still fermions. So yes, smoothness of the potential from Coulomb to infinitely differentiable. So the number of dimensions, 1, 2, I didn't even bother mentioning 3, and infinity for dynamical mean field theory. These various different kind of boundary conditions, which will turn out to be important. And the dimensionality, and especially the dimensionality, number of atoms, 1, 2, infinity. Here, the dimensionality. And in particular, we'll see in one dimension, there are a lot of tools that are available that are more complicated, let's say, to use in 2 and 3 dimensions. And in particular, we have this WKB theory from long ago, which gives you approximate semi-classical results. So if you think if you made a 5-sided cube, right now, which is a bit tricky in 3 dimensions, 5-dimensional cube, and then just each one of these is 3 grid points, right? There's already 243 possibilities. So this is part of my excuse for why it's taken me 12 or 13 years to try to figure this out. There are many different places you can look at what is going on. Okay, and the simplest case, which I will focus a lot of the time on, I call them SNFs. I mean, same spin, non-interacting fermions in boxes, or we'll put them in real potentials, but with infinitely differentiable potentials, and usually with just one minimum. So this is the simplest. You take all these things and look in one corner, and but the crucial part is that you have some, in a sense, a broad class of V of x's, right? You must be able to vary the external potential in a non-trivial way. Okay, so I'm going to go, this is 2 different ways, and this is part of trying to unite the people with different backgrounds. And so in the math mode, or I shouldn't call it math, I should call it sort of mathematical physics and the semi-classical physics, basically. You know, we look at this very, very simplified case to see if we can understand what's going on, right? And the argument is that if you can't understand this case, right, you don't understand the real case, which is much more complicated. But as I go along today, I will also we will take results from here and use them to get some insight. So we want to take them all the way from little particles in boxes to the real world. And I'll show you some examples of that to motivate, so that the electronic structure people don't fall asleep, right? It is relevant. Okay, so now I finally got to my outline after only 10 minutes, right? So first part, I'm going to look at the boxes. Then I'm going to show you some applications in the real world, and then I'll sort of go back to these one-dimensional systems. Okay, and yes, you can. We have Curon's rules in operation, right? You can bug me, but I'll be done by 12, right? One way or the other, and we can always have discussion later. So how is DFT related to semi-classics, right? So this is a quote, right? It isn't your usual sort of Dirac quote. It's, you know, so, you know, you get all the results solving the Schrodinger equation by simply evaluating one integral, right? Think of the local density approximation, right? Except this is from Griffith's book on quantum mechanics, and it's a chapter about semi-classics, right? And he's talking about the WKB formula, right? So this is where we take, this is the classical action at a given energy in some potential, in a simple potential, and we'll have box boundary conditions at first, and you simply, actually, you don't put in a Maslov index, it's just pi times j when you have box boundary conditions. But this very simple integral, right, gives you approximate eigenvalues. Sound a little familiar? Okay. So if you go back to the original Kohn-Sham paper, and you also sort of read a bit about what they were thinking about at the time, it's very clear that they were thinking of simple metals, lithium, sodium, the valence electrons in simple methods. Walter very clearly stated he never expected this density functional theory to work well outside of that domain. And why were they thinking of that domain? So you take so here's my 1D example. Here's the potential. And you assume that it's slowly varying, right? And the density will be slowly varying, nice and smooth and everything. So you fill up the levels past the potential. Here's a chemical potential. You occupy things, the Fermi energy, and you get some density like that. And they do the gradient expansion with this idea in mind, right? But subsequent history sort of showed that the local density approximation that they suggested in that paper worked rather well for many, many purposes. It wasn't energetically accurate enough, but it's extremely reliable, and it gives you very good geometries, typically, and so forth. So people use the local density approximation for a generation, not to do thermochemistry, But this was the picture that they had in mind, and all these old papers talk about this gradient expansion. Okay, now we're going to do this quickly in one dimension, just to show you the formulas and so forth for non-interacting particles. So you can just very simply, you can do these as roughly as you like. It doesn't really matter. You'll always get the same answers. So the density is the sum of the squares of the orbitals, and you get this very simple term here. So this is, this is the Fermi momentum at the Fermi energy, and the kinetic energy ends up being kF cubed. And so if I insert this guy into that guy, I get T of x is proportional to n cubed. And that's the one-dimensional analog of the Thomas Fermi formula for the kinetic energy, which is the 5/3. Okay, it's the same thing in one dimension. And you choose the chemical potential to normalize the density. Okay, now I quickly did this morning. I want to give you an example that you can do. Students, this could be homework. So you take the particle in a box, a flat box, to give you the simplest case, and you calculate the density. You occupy the first, so these are these sniffs. You occupy one particle for each orbital up to n orbitals. And if you look at your baby quantum book, right, it tells you that it's just sine is the wave function. So then the density is the sum of the squares of the wave function. And if you're good with your geometric sums, and it takes a little trick, right, you can do that sum explicitly. And you get n over L, a constant, that's a red line there, and then a correction, right? And the red line, you see, is yes, constant. It doesn't satisfy the boundary conditions. It's missing the oscillations and things like that, just like regular Thomas Fermi is for atoms, right? And there's a correction here. So if you do it exactly, you see this correction, but to get it in closed form is a bit tricky. An important concept is going to be the idea of uniform approximation. So there is no mathematical expansion of n of x, the density, in h bar, or 1 over n in this case. So large particle number is the same as h bar getting small for these simple examples. But a crucial point here is at different positions along this curve, right, the corrections will be of different orders. So you can see in the middle that as n gets large, the oscillations are going to get smaller and smaller. So you would say, oh, they're of order 1 over n. But notice that at the edge, the correction is of the same size as the density itself. So in different regions of space, you get different behaviors. And again, you get a different behavior in these boundary regions than you get from in the bulk. But a uniform approximation is one where the relative error goes to 0 everywhere in space. Now, we don't need an approximation here. This is the exact answer, right? But so we got a formula, which I'll show you in a minute, for, so this is the work of Attila Changi, Peter Elliott, and Dong-Hyun Lee. And so we tested it on this potential here, which is a double well inside these box boundary conditions. So let me show you the formula. So it took us about a year to figure this out when we first realized the nature of this problem. And so there's the Thomas Fermi density with a classical momentum. And so this is for an arbitrary v of x, right? So we get these quantum corrections that you can deduce from, you take the WKB formulas for the wave function in one dimension, and you sum over n semi-classical wave functions. But you have to do this very, very carefully. There are all sorts of things that can go wrong. It took us a while, but we finally teased out the right formula. And this formula has all those properties, and it is a uniform approximation. It will give you the right answers. Okay. So, and if you stare at that formula, you can see it's constructed from standard elements of semi-classical physics. So for example, a crucial role is played by the time at the Fermi energy. So you look at the Fermi energy, and the time it takes to cross the potential shows up in the final formula. It's very, very delicate to make sure that it all comes out right. And this correction, so that the first term is Thomas Fermi. It's a perfectly ordinary local approximation in the potential. But the second term is highly non-local. And this only works, our derivation for this only works when the Fermi energy is above the potential everywhere. And notice that you only ever evaluate the formula at the Fermi energy. So as the number of particles gets larger, you're using semi-classics at the energy of the highest level. In fact, one beyond it, it turns out, rather than for the individual levels. And that way you always get a more accurate answer, in fact, than any kind of WKB treatment of individual levels. Okay, so now we tested it, and we took a potential here. It's a double well potential, but we have to have so the zero of the potential is there, the hard walls are there, and we put in 4 levels. And in fact, there's almost a degeneracy here, but then 2 more positive energy ones. So here is the 4-level density with the wiggles and everything, and this is the Thomas Fermi result. And the Thomas Fermi energy, I think on the self-consistent density, is 153 Hartrees. Sorry, that's on the exact density. On the Thomas Fermi density, it's 115. So that's showing you, that's a measure of how wrong the Thomas Fermi density is. And you see, again, it doesn't obey the boundary conditions. So when we add in the corrections, on the semi-classical density, if you evaluate the Thomas Fermi energy, suddenly it's better by about a factor of 40. So the error goes way, way down in that density. So we're just using the Thomas Fermi functional to measure the energy and the density, but we also had a formula for the kinetic energy density, which is comparably good. And notice also that, so the new density is almost right on top of the black line. And notice this difference in accuracy, right? And I'd never had it happen to me before, where I sort of write down some approximation and we just try it out, and it's 40 times more accurate than the existing one without any parameters. So this is really important, right? This formula was derived as an expansion in h-bar. There's no fitting, there is no exact conditions were used in the construction of this formula. In fact, it even violates, see this delta n, we didn't even make it the density integrate to n particles because we just took the formula as it came out. It can probably be fooled with. Okay, switching now to the real world. So I have this sort of cube here. That means implications in the real world. It's red, right? So you can relate all this stuff to this semi-classical limit, which applies to all matter, atoms, molecules, and solids. The simplest case is, say, neutral atoms, and it's taking z equals n to infinity for neutral atoms, and Liev-Simon proved the relative error in Thomas Fermi theory goes to 0. So what we want, but chemistry and most materials actually do not look like the picture that Walter and Lou Sham had. In fact, the chemical potential usually cuts the Kohn-Sham potential. We would now call it the Kohn-Sham potential, which means that you get isolated densities and you have evanescent regions in between. So this is what a 1D Thomas Fermi theory gives you. And then you need to put in, the oscillations and things to get a more accurate description. Thomas Fermi theory is useless for modern chemical accuracy. Okay, so it's still relatively exact in this limit. And of course, in the real world, we have turning points. We don't have box boundary conditions. So I sort of conjectured that this would also be true. The Kohn-Sham analog is that the exchange correlation energy error goes to 0 as you go to this limit. And in the few numerical cases we're able to do this, in fact, it turns out to be the case. Exchange is very straightforward and very obvious. Correlation is much more subtle. But it looks like we can show that, so we argue this here.
What's this parameter zeta again?
So zeta is just, I like to use dimensionless parameters, so I put zeta in front of z. But when I have a real system with bond lengths and things, also the bonds squeeze up with a zeta to the 1/3 as you approach this limit. And you have to do that exactly right to get a non-trivial limit as zeta goes to infinity. Thomas Fermi scaling is what we... The only reason I don't use that term is some people then assume it means something approximate, because Thomas Fermi. So it's very tricky, by the way, talking about this to all you guys, because you all speak different languages, right? Okay, now real-world implications, and I think I'm going to skip a bit in a moment, right? So it explained why the GGA needed to be generalized. It gave us the parameter in the Bekke-88 functional. We could derive it, sort of, from first principles, right, without any fitting. And PBE-SOL is something that came out of it. There are two conditions used in this PBE-SOL, and one of them came directly from this semi-classical analysis, from realizing that your exchange, you know, what we built into PBE-SOL was to recover, what we noticed in PBE exchange is that it almost gets this asymptotic condition exactly right, that as z goes to infinity, it gives you the leading correction to LDA. When we realized that was necessary in order to get good thermochemistry, we then threw it away and restored the gradient expansion for exchange. And I just want to show this picture. I was at a meeting in material science. They'd never heard of these things. And at the first day, they showed, oh, LDA and PBE, the answer is probably somewhere in between. This is the bulk modulus. This is the lattice parameter. And LDA has characteristic errors with too small a lattice parameter, too big a bulk modulus, and they were making the point that PBE overcorrects in the opposite direction, right? But they had never heard of PBE-SOL at the time. It had only just come out, and they ran it that night. And then you see that PBE-SOL improves geometries and properties related to derivatives, but its energies are not good, right? Oh, no, this is comparison to, these are the errors in the bulk modulus and the error in the lattice parameter. Yes, exactly. So, and these are, you know, a few percent in the lattice parameter and a bigger percent in the bulk modulus, but, you know, that's when you're stretching it in in 3 directions at the same time. Are we doing okay? There's a lot of stuff here, right?
It says aerosol due to exchange variation. There's some pseudopotential involved, right?
In this case, I think those errors are probably, yes, well, I mean, they'd be typically at the 1% level, I think. Yeah. Yes, I think they were running VASP. So there are certainly more accurate results than this. This was 10 years ago or whenever, 6 or 7 years ago when we did PBE-SOL. Okay. Now it's a topic that came up during the week. I sit in the chemistry department. I teach chemistry to undergraduates. This is our typical picture of the ionization potential, right? For the mathematicians, this is a periodic table here. So as we go across a row of the periodic table, you see this pattern where the ionization energy is biggest for closed shells and smallest when you've got one extra electron sticking out. But you see this pattern for noble gases. You see the ionization energy is sort of slowly going somewhere, and here for the alkalis, it's going somewhere. So this is the real periodic table up to about 100, right? So we decided, so the important question we were interested in was, well, we know about these Lieb-Simon theorems for total energies. All of chemistry and material science cares only about energy differences, and a lot of the success of the functionals is for the differences. So what we did was we took an imaginary atom, turned off relativity, assumed the Madelung rule applied everywhere, and this is work of Lucien Constantine and a graduate student, John Snyder. And we went up to 3,000 electrons, but then we extrapolated to the infinite electron limit. So you see the scale of the numbers is now a lot smaller by a factor of 2 or 3 from the actual elements, but you still have this structure going across a row. So this is 1, 2, 3, and these guys here, 3 to 8. And you see that you have this pattern. Now look first at this line here. Well, there are 3 lines together. So the black dots are Hartree-Fock calculations, so that's at the exact exchange level. And the 2 sets, the blue and the red, are, and I don't know which is which, LDA is red, PBE is blue, and you see that, and these are within the level of the extrapolation, but you see that they are essentially right on top of the Hartree-Fock results. So what that's showing is that these local the fact that PBE gives you the same as LDA is telling you that the gradient corrections are not affecting the answer by definition. And then the LDA is exactly matching the exchange calculation for the ionization energy in this limit, right? Now, from Heinz's point of view, we were discussing last night or the other day, about the total energy of the atom as Z goes to infinity. The ionization energy, if you think about it this way, is the difference between the atom and the neutral. And we have that expansion in powers of zeta, third powers of Z, right? But this is a finite number as Z goes to infinity, which means the first, I don't know how many terms are canceling between the neutral and the ion. Okay, and then we look at exchange correlation, right? And this was the result I mentioned. So we have LDA and PBE. It's not possible. Don't believe any quantum chemist who tells you they can do this calculation. But we can do it with Kohn-Sham DFT. And you see, again, the numbers are within the error on top of each other. And John and I could not understand at the time exactly why they're on top of each other, but the fact that they're on top of each other is very suggestive that the local approximation is again becoming relatively exact. And these are, therefore, if we could do the calculation exactly, it would again lie on top of this curve. And this is the Z goes to infinity limit of the ionization energy. And now this is across just these 2 rows. The row actually is huge by the time it's the 24th row at 3,000 electrons. But if we average across those rows, we get almost exactly this 3.15, which comes out of that book of Burgess, 30 years ago. Incredibly, right? Not Thomas Fermi theory. You have to put in a correction, the usual corrections of von Weizsäcker and Dirac, and you get this number, which I suspect if we could have done all the way across the row and averaged them all, we would get that number. And as I mentioned, there isn't a quantum chemist alive who can explain to you how on earth that is possible, right? Okay. And here, even if you look at the ionization density, the density difference between the neutral and the ion, you see that you do this fully quantum calculation, and the envelope of this density is approaching. You got lots and lots of oscillations, but it approaches the Thomas Fermi result. Okay. So heuristics of density functional approximations. So I claim there is a systematic expansion. This is all telling us this, and it looks like in these very simple model cases, getting these corrections right gives you very, very accurate results. And getting these corrections right has been going into modern functionals. And this is one I'll go over. I'll just mention it very quickly. We took the correlation energy of PBE and we nudged it slightly with some exact conditions and so forth to make it now be asymptotically correct. It used to be close to it, but not quite right, and now with this little nudge, it is.
Goes to infinity limit. You're assuming that the system is localized in space.
There's no assumption. Yes.
You get exact results for all
Yes. As I said, atoms, molecules, and solids in this limit. But then the bond lengths scale in a very specific way. But it's well defined for everything and things. Okay. And there's a paper about that last year by Tony Cancio with this modified GGA. And also we had some discussion of this potential functional theory. And we just, so in all of these cases, right, in the one-dimensional cases, what had we done? We'd gotten the density as a functional of the potential, semi-classically, right? And we just showed here and then tested it with calculations that, in fact, once you know that relationship, you can actually deduce the energy. And this is using the theory of Whitehouse and Ball-Ayres and so forth. Okay. Now I'm going to switch gears. I got about 10 minutes left. Yeah. Okay. More recent work. So this is in the last few years. And this is work I'm very proud of. So we got stuck when we tried to do real turning points. It turned out to be much harder. We guessed lots of formulas. They weren't the right ones. We had to sort of really derive it. And I happened to be in Bristol, and I got a couple of hours with Michael Berry, and I tried to explain to him what I was doing, and he mentioned this statement from his third paper, right? I was rather young when this came out, so I don't think I read it at the time. So use the Poisson summation formula, right? So the trick is you take a uniform approximation, which is, you're using the Airy functions to go through a turning point for the wave functions, and then repeat our exercise, right? So I was very fortunate to have Rafael Ribeiro, who's sitting up there, as a graduate student at just the right time, and after, 2 or 3 years, I think, right? And if it took him 2 or 3 years, it means it wasn't easy. So this is the solution to a 50-year-old problem. The people who had worked on this before, among others, were Kohn and Sham before they wrote their famous paper. But many, many people in nuclear physics, Bragg, and in quantum dynamics. And they'd all kind of gotten partial answers, but Raphael got the right answer, which is a uniform approximation for the density when you have turning points, right? And this is a Morse potential case. And we put 2 particles in, and the reason, so there's the Thomas Fermi line, which is just that piece. And then you have to be really good with your mathematical physics to get this. And you can't see the difference between the black and the red lines because the approximation is that accurate. Your only chance of seeing an error is if you just put in 1 particle. I'll show you one case. And so we did all that work. And here's the semi-classical formula for the kinetic energy. So this turned out to be much harder. And if you like this kind of thing, we'd be very happy if you would read some of these things. So the level of math, I would say, was just a little bit beyond us. And we were using some new relations among Airy functions that people hadn't used before. And what we tried to do was clearly state each spot where we had not been rigorous, right? So there were a couple of places where we could see how the functions go, but we weren't able to prove it. And by prove, I mean a physicist's proof, which to the mathematicians here means not a proof at all, but you know what I mean, right? Yes, and we had a lot of fun with that. Okay, and like it's just, this formula that Raphael got is like It's just incredibly good. It's sort of like that formula for the ionization energies, right? So in these cases, we took something like a delta function or very close to it, and it still works. And here we have a double well potential, and we calculate the density in between the two wells, right? So this is the Thomas Fermi density, and this is our new density. And once again, it isn't that your eyes are old. There's a blue curve and a red curve, and they're right on top of each other. So, from my point of view, it is very, very weird that we can get essentially almost the exact results of quantum mechanics, and we don't solve any differential equation, right? What goes into these things are classical phases, nothing else, and Airy functions. Okay, so I'm going to finish, so there'll be time for questions, with a catastrophic failure, right? So we were so thrilled when we got this thing, right? And we wrote it up, and we were very, very happy, and then we would sort of go explore it and things like that. Except it turns out that, well, when I realized what had happened, I was a bit upset, right? So when we did numerical tests on various simple potentials, so we'd take these beautiful formulas, and we could see that they were way, way better, and we would extract the actual energy. And sometimes it was better than Thomas Fermi theory, and sometimes it was worse. And like, how could that even be possible, right? So Raphael did a lot of very, very careful numerics. And what we found was that regions in the parts contributing from the evanescent region were canceling bits coming from the traveling region. And in fact, we were able eventually to prove that, in fact, these contributions canceled exactly. So we had done all this work to get these corrections. And let me I'll show you this picture, right? This is a harmonic oscillator. Now, somebody had printed some homework problems, handwritten, but I don't know who had written them. On the printer, I saw them. You do the harmonic oscillator in a Thomas Fermi calculation in one dimension, you get the exact energetics, right? That means any correction you put in, if it ain't zero, it makes it worse. So here's our kinetic energy density. So I put one particle in, and I can see the difference between the blue and the red, right? One of them is exact, one of them is approximate. As soon as I put in more than one particle, I cannot see the difference, right? This orange curve, this green curve, they're right on top of the quantum mechanics. This is 4, I think, and this is 16. That black line there is what I would call the stupid Thomas Fermi curve, right? And you can do this, you get it with it takes 2 minutes with a pencil and paper to get that curve. But because that curve gives you the exact energy of a harmonic oscillator, it's better than the blue curve, or whichever one is the approximate one, right? And what's happening is you see, actually you don't see it clearly here, but there's this cancellation of the errors. It must happen further out there. Okay. So that was like, I'm about to finish. So you could show that the derivation, you could show that you needed 3 more orders in this derivation. Now, I did briefly consider postponing, Raphael's graduation for about 2 decades, while he can, having done this heroic effort to solve this problem that people had for 50 years. And even Michael Berry was impressed, but it turned out not to solve the problem that we wanted, right? It means that our box boundary conditions were very misleading, right? Because when we take the formulas in the box case and integrate them up, we get the leading correction. We demonstrated it for the box problem. So that was good, but then this turned out to be, so this just seemed evil, right? So we had obviously, in hindsight, right, we had oversimplified the problem. you could say, but who could have known, right? Okay, so outrageous claims, which I will put some flesh on, right? So I'm giving a public lecture on Tuesday night, and I'll talk about saving the planet using semi-classics. I would say almost no one understands this.
A week from today.
Yeah, not tomorrow. Yeah. And so these are slides from a talk that I gave, a physics seminar in Bristol, so I was the visiting professor there for the last 5 months. Now, I was supposed to, just, go on sabbatical, chill out, relax, chat to people, have a nice time, get the pressure off and stuff like that. That was my plan. And actually in Bristol, it's really nice. They have a very nice visiting program and all that kind of stuff. It didn't quite work out that way, right? I would say I worked harder in the last 3 months than I have for a long, long time. And also could be the death of your academic career, right? So these were slides I made 3 months ago giving the seminar in Bristol. And the reason is it's such a hard problem, right? But what I'm going to, so summary is, well, we didn't really go through much of that because we hear about it all this week, this lead assignment, right? And yes, I could use help. This is what I put on the slides. And I say, I got some help. And I got some help, and I think we now know how to resolve all of this stuff. And thanks to everybody for listening.
Discussion. Here's a question.
You have results for one-dimensional systems, but you could also do similar things for three-dimensional system with spherical symmetry, I guess. Now, with semi-classical approximation, things are already slightly different, right? Instead of L times L plus 1 angular moment, you get L plus 1 half squared.
Yes.
All those little tricks.
Yes.
So now the question is, how would those results that you showed translate to 3D with spherical symmetry?
So that was our plan, right? And so there are complications because for Coulomb potential, the 1 over R, say for the S states, there are issues as R goes to 0 semi-classically. And of course, when L is not 0, you have the centrifugal barrier. So all of these are varying rather rapidly. And sort of basic semi-classics has issues there. So our plan was absolutely, and we had actually done a bunch of numerics. So we were going to sort of demonstrate things on atoms and ions, solve them, the spherical part semi-classically, when we discovered this failure that we were not beating Thomas Fermi theory in one-dimensional cases. So we have a pile of stuff. We didn't do it analytically. We had a pile of stuff sort of numerically, and we simply never got back to it because of this issue of, so what we found was, so we were getting insanely accurate densities, insanely accurate kinetic energy densities, but not, our results were not much better than Thomas Fermi theory. Sometimes good, sometimes worse, right? And so that part of the program, we just came to a halt right there. So it is an exercise, and it could be a complicated exercise to attempt to apply the 1D formulas in Raphael's paper to the spherical case. I mean, it's a very interesting topic and would be very useful to know the answer, right? But then you have to face the Coulomb issues, right? But should be straightforward to apply them. They fail, you try to fix them for those issues, and then maybe you get really good results. Densities, but that's just atoms, right? Spherical objects.
Great job.
I have 2 questions.
Yeah.
One is, can you explain how when you get the not good, so good total energy, how do you get the energy and how do you get the kinetic energy?
Yes.
Can you explain how you get the density?
Yes. So in each case, right? So So your density is the sum of the squares of the orbitals. Your kinetic energy density, you can use any gauge you like. It doesn't matter. You apply the techniques. So let's say you take the positive one. Actually, I think we were doing the phi del squared phi one, that one. And you do the same analysis. And we didn't quite get a proper uniform approximation in the box boundary case, but we did get one for the real turning points, which is sort of more important. So it gives you, so I only showed you formulas for the density. There are absolutely analogous formulas for the kinetic energy density, and then you just integrate it numerically to get the kinetic energy, right? So these are all as functionals of the potential, right? Of course, you later want to turn them into density functionals, but there's no point if their energetics are. So, by the way, I want to emphasize, right? So people ask me, am I a physicist or a chemist? And my answer is always yes. But then I ask them, well, how can you tell if you're a physicist or a chemist? And there's a very simple way. You look into your heart and you say, if I'm a physicist would rather be right than useful. Now, I hope I've insulted both physicists and chemists if you think about all the corollaries of that statement. So a big issue here is there are fascinating mathematical and physics issues involved in this. And you try to talk to people like Heinz and whatever, and you have a really good time. But, so I stopped the whole line of research when I realized we weren't getting better energetics. Because the point is to improve the density functionals that people use in the real world, right? And so if we're not getting energetics, it doesn't matter how good all the rest of our... Now, all that stuff can be used in many, many contexts for tunneling and all sorts of things. But, yeah.
So
Yeah, sorry.
There are a couple of questions. So there in the back row was the first. Yeah.
Is that Lior?
The first.
Yeah.
Yes.
So two follow-ups on what you just said. One of them is related to the practical aspect. So if I look at those ACGGAs that you showed,
Yes.
how would they perform in practice compared to conventional GGAs? So
How would they perform?
in practice compared to, say, PV?
Well, so the nudge is very, very slight. It turns out that the exact conditions in the correlation energy of PBE really don't determine the behavior in the sort of asymptotic limit well enough. So there's this freedom, which I seem to remember making this picture 25, 30 years ago, whenever it was. But we didn't do anything about it. So we could go back in and do this nudge to make it asymptotically correct. I suspect it would have very little... Oh, and we checked some molecules. And sort of interestingly, so it didn't really improve the performance, although when you made a hybrid, you needed less exact exchange to get the same accuracy as PBE 0. So it was kind of interesting. So it is a little bit different, right? But the big differences should be when you go to heavier atoms. And people like Angela Wilson are trying it out to see if bonding and of course, then you've got to turn on relativity and all that. But I mean, using this asymptotically corrected to see. So we did, the usual first row organic-y kind of things. And so, didn't see much difference for the molecules. But then afterwards, I realized, of course, we should have gotten involved with somebody who does heavy elements. And then it could be important. Yeah.
My second comment is about the difference between chemists and physicists. But another difference is that chemists don't know enough physics and are ashamed of it. And physicists don't know enough chemistry.
And they're proud of it, yes. Absolutely, yeah.
Okay, so let's
There's
not go to
Sergey.
philosophy now. Okay, so there's one.
Sergey.
Sergey is
Yeah.
the next question.
You can have, or you can look also at the semi-classical equivalent of some eigenvectors, right?
Yes.
And that gives you pretty much the kinetic energy. So does it behave if you just change the box size or change the shape of the well? Does it
Well, I'll talk about the semi-classical sum of the eigenvalues on Friday. But I mean, these things will outperform, typically they'll outperform sums of the WKB energies, these formulas, yeah. And this actually, so this is related to the fact that you only ever evaluate them at the Fermi energy. So as the number of particles grows, it way outperforms the WKB energies because they have the errors down. So this is the actual whole mathematical trick going on in these formulas. Yeah.
You're saying that this outperform WKB eigenvalue sum?
As n gets large, absolutely.
We have a couple
Yes,
of questions
yes,
here
so-
to be asked. Please don't just go into the discussion. So Mel, you have the next question.
Mel.
Talk about being proud of not knowing. The danger to the world is when those in power say, I'm proud of not knowing any science.
Yes.
So I think, Bagger, you have the next
Oh,
one.
well, I think my question has been answered really well.
Okay. Further questions? Heinz.
And
You put these particles in the box, meaning that you put theoretical boundary conditions.
yes.
Right. Have you considered other boundary conditions, like normal boundary conditions, and do the same computation?
No, you know, and one could, right? Absolutely. So
The difference was so big because you forced everything to zero.
yeah, so in hindsight, it sort of becomes clear. You can think about these box boundary conditions as being potentials of infinite gradient. And so they're different in the semi-classical limit than things without that, right? I mean, that's one way to think about it. Yeah, I don't know, right? Well, Andreas is next, wasn't he? Sorry, yeah. Sorry.
The correct is that you compare with uncorrelated systems, sample forms, that exactly.
So in the one-dimensional parts of my talk, it was only non-interacting particles. In the middle part, I showed, for the ionization problem, I showed comparison with Hartree-Fock of just the exchange part of the density functionals. I forgot to say that. And then we turned on correlation, but we don't have an exact calculation.
I think when we look in kinetic energy density, are the errors of the same order of magnitude as the correlation error or no?
Sorry?
We have the correlation contribution of the kinetic energy density.
Yes.
Would it be of the same order of magnitude as the error, the indistinguishable error there? Or
Well, again, as I say, the integrated energies here are not much better. Sometimes they're better, sometimes they're worse than Thomas Fermi theory.
the part of the energy what's better. Means that you don't get this object, but you say I collect only this part of the energy.
Yeah, we can discuss after. Yeah.
Really quick question.
Yeah.
You have uniform approximation for a total density, but the question is, do you have also analogous approximation for individual orbitals with large quantum numbers?
So there's about a dozen or so papers that we've written on this topic over the last 10 or 12 years on my website, but sadly I've never written any kind of review or summary, right? But they represent about 25% of the work we've done, right? So in the unpublished work, we have a paper that looks like a paper, it's a draft, right, from a few years ago, but never submitted, in which we deduce the densities of the individual orbitals by subtraction, because I can do n and n minus 1 and get each one.
Well, but you still get uniform approximation, that's a question.
Oh, do I still get a uniform? Well, I don't. That's a good. That's a nasty question. I think in the region of the node, we have an issue, because if you don't have the node in exactly the right place, it won't be a uniform approximation. And I think, in fact, our things would sort of dip, but they don't get the nodal region quite right. I think they might even sort of go negative because it's a difference. They're extremely accurate, but not right. They don't satisfy the conditions of a uniform approximation, which makes sense, right? Because it's a difference of two. Yeah. Very, very advanced question, Jerzy.
So I think it's
very
time
good.
to close the discussion.
Yeah.
Thank you very much.